east of the Mississippi River. So it's a 256-foot waterfall. And this is actually in an area where there's many other waterfalls. It's not the only one. There's several really pretty ones to look at. If you have bikes, I would take bikes to this area. There's several bike trails. And the hiking that we did was not extensive. It's kind of flat. So I don't know if you're asking, can you hike down to the bottom of the waterfall? I don't know. We didn't do that. But there is a good hike around like the rim area. What I mean is like in through here. So if you like cliff ledges, then this one is a good one to hike. But anyways, Fall Creek Falls in Tennessee. Okay, I'm going to switch my screen back this way because you can see the whole slide better. All right, we're going to talk about solutions. And that's chapter 9. Then chapter 10 is acids and bases. And then we might do a touch on functional groups in chapter 12. And that's it. That's all the material for this class. So we are nearing the end. Hang in there. You're all doing great. And I know you're giving it your best. So solutions, what are they? Well, I don't know if you recognize this figure. This figure we saw like the very first week of class, and it just was helping us to classify matter by kind of sorting it out, categorizing it out. So we had the question, if we have some kind of matter, how do we classify it? And so we would ask these questions like, well, is the composition constant? Yes or no? If the composition is constant, then you're looking at like elements and pure substances, okay? Compounds like water or sugar or different elements, those are pure substances. But if it's not constant, if it has a varied composition or a non-uniform composition, we call that a mixture. And a solution is a mixture, okay? Well, remember there's two kinds of mixtures as well. There are heterogeneous or homogeneous mixtures, okay? Homogeneous mixtures, you know, my favorite example is ice cream, and a homogeneous mixture would be like vanilla ice cream. Also, side note, I'm trying to go dairy-free for a week. Anybody had to ever go dairy-free before? If you do and you have any good dairy-free hacks, please let me know. And here's why I'm not doing it for me. I'm doing it for my son because he's got some bad eczema. Babies can have that sometimes. So any eczema people, if you have tricks or tips on that, or any Kato ice cream. I'm dairy-free. It's not too bad. I don't think I could do that. It's hard for me. I'm not a dairy-free person. I love cheese. I love all sorts of dairy. But anyways, I'm trying it. So email me your tips on dairy-free if you have them. So anyways, talking about ice cream, vanilla ice cream is an example of homogeneous. Every bite tastes the same. There's many things in it, but they're all mixed uniformly. If you throw some Oreos or some candy or whatever in it, now you have a heterogeneous mixture. But a solution is a type of homogeneous mixture. So the examples you see here would be like salt water, seawater, gasoline's an example. And then you also, another kind of heterogeneous mixture, we call it colloid. So milk is an example of a colloid. And the difference between a colloid and a solution, what's the difference here? It just has to do with the size of particles, okay? The size of the particles is what differentiates these. Solutions have smaller particles, okay? The molecules or the things in a solution tend to be more like ions versus actual molecules. And in a colloid, I mean, think about milk for an example. What things are in milk? Now that we're talking about dairy and not having dairy, what's in milk? What types of molecules are in milk? Anybody? There's many things in milk. Milk contains cream, okay? Yes, let's break down like the actual calcium, which is an ion. What non-ion substances? Lactose, okay, that's a sugar. So you have sugar in milk. Sugars are large molecules. Like they can be lots and lots, hundreds or thousands of atoms, okay? They can be very large. You've got protein in milk, okay? You've got water molecules in milk. So you've got some larger biological molecules in milk. That's all I'm trying to say. In solutions, you have more things like ions. Like, for example, seawater, you have Na plus and Cl minus. Those are ions. Ions are very tiny compared to things like sugar and proteins, which are in milk, okay? So the difference here is the size of the particles. Solutions contain smaller particles. And if you're wondering how small, this table down here actually just tells you the particle size. First, to be classified as a solution, the particles in that solution have to be smaller than 2 nanometers. Anybody remember what a nanometer, how it relates to the meter? How many nanometers are in 1 meter? I don't think this is one I ask you to memorize, but I'm curious to see. Yes, 10 to the power of 9. There's a billion, okay? 10 to the power of 9 nanometers in 1 meter. All right. So nanometers are incredibly small. So, anyways, there's the examples. And here's some characteristics of these solutions that we'll go through in just a second. But let's actually define what a solution is. It is we now know it's homogeneous. I don't know if that second E should be there. Yeah, it is. Homogeneous mixture of ion or molecule sized particles. It's a homogeneous mixture of ion or small molecules, okay, sized particles. So there's that. And then you can read some different characteristics between a solution, a colloid, and a heterogeneous mixture. I actually want to point a few of these out. So the top one over here this is the solution up top. Solutions are transparent. What does that mean if it's transparent? What is something that's transparent? Can you see through it? Can you not see through it? Okay, Aaliyah says see through. Genesis can see through. Yeah, transparent to light. So it's kind of, it may not be like colorless, but it's clear in the sense that you can see through it. Okay. Does not separate on standing. You can't filter anything out. Okay. The next one down, the middle one is the colloids. Okay. Often these are murky. Does not separate on standing. So what they're saying with a colloid is, let's say you pour some in a cup and you just leave it sitting there, you're not going to get like two separate layers. Something's not going to like settle to the bottom. But the last one down here on the bottom, heterogeneous mixtures, these are also not transparent, just like colloids. But what the difference between a heterogeneous mixture and a colloid oftentimes is that you do have something that will separate. If you just pour it in a cup and you leave it for several hours, you might have something settle to the bottom because you have particles that are that large, or portions of the mixture that are larger, and they'll settle to the bottom. So blood is the best example here. Can anybody name the largest component of our blood? Our blood has many things, but what is the largest component of your blood? Anybody know? Yes, Kathleen. Yes. Plasma. So our blood has several things. Let's actually write these out. Has plasma. And I think it's roughly, don't quote me on this, I could be off by a little bit, but I think it's just like 55%, 55 to 60% of our blood is plasma. What else is in our blood? What might settle to the bottom if we poured it in a beaker? That's a gross thought to me, but what else is in our blood that are larger? Okay. Yep. Kathleen said RBCs, red blood cells, and white blood cells. These are larger. A cell is larger than any protein or molecule of sugar, for example, because cells contain many proteins. So cells are larger types of, it's weird to call a cell a particle, but they're larger particulate matter. And those types of things, plasma, red blood cells, white blood cells, those would settle. Okay. Now, blood, if you removed all of this stuff, the plasma, the red blood cells, and the white blood cells, you would actually have a colloid. Okay. Because your blood also contains, here's some more things, proteins. Okay. And other large types of molecules, such like proteins. You have sugar. We know we can measure blood sugar. But then what else if you removed all the proteins and the sugar from your blood, what else is in your blood? Okay, you have air, you have oxygen in your blood, and you have ions. Okay, we call those ions electrolytes, and we're actually going to get to electrolytes next week. You have water. Okay, so these are the smallest things in your blood. These are the medium-sized things in your blood. And then over here, these are the largest things in your blood. Okay. So depending on, what we could or could not filter out of our blood, we could have a solution, a colloid, or a heterogeneous mixture. But when it's all together, like in our body, our blood is a heterogeneous mixture. Okay. What about platelets? Yep, Savannah, we have platelets as well. Platelets would probably settle to the bottom. I'm not exactly sure how large a platelet is, but they would settle, I'm sure, just the way plasma and cells might. So, anyways, I wanted to point that out because I mean, blood definitely relates to health sciences in so many ways. Anybody know their blood type? Anybody a blood giver? That's a weird phrase. Anybody go to Red Cross, donate their blood? I don't know if. Yeah, I'm O positive as well. Weird. So many of us are O positive. I forget. Okay, what's the universal acceptor? I gave blood last week and almost died. A, B, is it positive or negative? That's the universal receiver. I think positive. A, B positive. Okay. O negative is the universal donor. So I'm almost a universal donor, but I'm not. Okay. Enough about blood. If I talk more about it, I might pass out. That's just how I am. I get queasy around blood. When we come to solutions, though, overall, there are two portions of the solution, no matter what we're talking about. You have the solvent and you have the solute. Okay, now how are these parts? What are these parts? The solvent is the portion that's present in greater amount. And it is the thing that it's like usually, I don't want to say it's always the liquid, but when we think of solutions, typically they're liquid. And it is the thing you're dissolving the solute in. Okay, typically it's a liquid and it's what we're dissolving a gas or a solid in. So if you have salt water, water is the solvent. Okay, solute is the dissolved part. Okay, it's the ions or the sugars or the molecules. It could be a gas that is dissolved in your solvent. Okay, but a lot of people will box their mind into thinking that solutions are just liquids, like dissolving salt in water. Your solvent is the solid, and the solvent is the liquid. But I want to broaden your horizons for a second, because you can have all types of solutions. You can have so many different things. You can have gases mixed in gases. That's a solution. Anytime you're mixing two things and you have one present in greater amount, one in lesser amount, that's a solution. The atmosphere, okay, is a solution of gases. What else is a good example? A liquid and liquid. We mentioned gasoline was an example of a solution, and it is liquids dissolved in other liquids. You just have some present in larger amount and some present in lesser amount. What else is a good example? Gas in a liquid. What's an example of that? My favorite, fizzy water. I call them fizzy waters. Okay, club soda. That's an example. CO2 dissolved in water. LaCroix, all right, is an example of that. But any soda, Coke is an example, right? You got CO2. Nasty water. I used to not drink in college. I did think it was very gross, but I now enjoy it. Okay, but here's what we're more familiar with: solid and liquid. Okay, seawater, NaCl, and other types of salts dissolved in your solvent. All right, so anyways, I just wanted to show you this table because there's all different kinds. So don't box yourself into thinking it's always some sort of solid dissolved in like sweet tea, sugar dissolved in the tea. Okay, it's much more than that. All right. Now that we've identified and we've defined what a solution is, we also need to consider that with any solution there are limits. Okay, when you are dissolving something in a solvent, your solute, there's limits on how much you can dissolve, and then at some point you reach what we call the solubility limit. So when we're thinking about this, we need to identify one. When do we know we're going to get a solution? When do we know when something is or is not soluble? Okay. How do we determine when you're going to get two things that mix? I got ahead of myself with the limits. We'll get to solubility limits in a second. But not everything, just because you put two things together doesn't mean they're going to mix. Anybody think of an example off the top of your head that if you mix two things or if you put two things together, you know they won't mix? I'm thinking of salad dressings. Anybody, your favorite is like oil and water. Okay. Balsamic vinaigrette or something like that. You have to like shake it up. It's my pet peeve when you have the two separate layers and someone just like pours it. You get like all oil, or all vinegar, and you don't get the actual thing mixed together. So we have a phrase that we can use when we're determining when something will be soluble, and it's this right here: like dissolves like. Like dissolves like. What does that mean? One, it's an easy little catchy phrase to remember, like dissolves like, but that is really, it all goes down to the types of intermolecular forces at play. So I hate to bring chapter 8 back into the conversation, but everything we learned in chapter 8 about the types of intermolecular forces and identifying when something is polar or nonpolar, that applies here. Okay. Polar substances, polar solutes, and things that are ionic, because really something that's ionic is so polarized that you have a permanent separation of charge. Okay. Polar things are just a semi separation of charge. Ionic things are like polar on steroids. Okay. So polar and ionic things will dissolve in polar solvents. Polar and ionic solutes will dissolve in polar solvents. Polar dissolves in polar. The best example there really is salt and water, NaCl. We know that's ionic. And water, H2O, we know water is polar. Okay, so anything that's polar, anything that's ionic, will dissolve in a polar solvent. So you have to still be able to identify. Don't forget how to determine if something is polar or nonpolar. You have to know how to do that for chapter 9. Another thing, nonpolar dissolves in nonpolar. Okay. So oil and gas. My favorite is soap. Soap is a very alkaline. Those are typically nonpolar things. We know that soap and water typically they don't mix very well. But soaps oftentimes will, if you can't get something out with water, you can use soap a lot of times, and it will get that grease stain or something out, because we know grease is a nonpolar substance. Grease and water don't mix. It's very oily based. So soaps and grease, soaps and different kinds of stains will mix because they're both nonpolar. Okay, so nonpolar dissolves in nonpolar, oil and gas. But this last one here, polar things will not dissolve in nonpolar. Okay, so if you have, well, the example gives us oil and water, right? We talked about that. Polar does not dissolve in nonpolar. So I actually have a poll question on this, and I almost forgot, but I have my reminder. So let's actually, I want to see here. Let me find the right poll. Okay, so I'm going to launch this poll, and what it says is, based on the concept like dissolves like, which of the following solutes would be soluble or would dissolve in acetone? So you have CH3, and then you have a carbon with an oxygen, and then you have another CH3 group. Now, acetone is polar. Okay, we actually used acetone as an example when we talked about dipole-dipole interactions. We said acetone is different from molecules that are just made up of carbon and hydrogen, and therefore it's polar, and it would be held together with dipole interactions. So look at these 4 options: CH4, carbon tetrahydride, a molecule of chlorine, Cl2, a molecule with carbon and hydrogen only, a carbohydrate, and then NaCl. Which molecule would dissolve? Okay, so if acetone's polar, you need to ask yourself which molecule here is polar. The one that is polar or ionic would dissolve in acetone. We're about halfway there. 20 of 26. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. End poll. All right, 92% voted. Share results. Okay, so most of you got it. The largest portion of the votes went to NaCl, and that's correct. NaCl is ionic, so it will dissolve in polar solvents. Okay, so acetone being polar, NaCl would dissolve. None of those others are polar. Okay, if you drew the Lewis structure out, you would see there's either symmetry or the molecule is entirely made up of nonpolar bonds. For example, C2H6 is entirely nonpolar bonds. So, okay, good. Let's go on to the next thing. So the basis of this, the basis of like dissolves like, this figure is from your textbook, but I think it's a really great picture to understand why do polar things and ionic things dissolve in polar solvents, and then vice versa, nonpolar and nonpolar. Well, it has to do with the type of, again, intermolecular forces at play. And the intermolecular forces here are represented by these dotted lines. So let's read this statement. A solid will dissolve in a liquid when the solute solvent, there's our phrase, intermolecular forces, are similar to the solute-solute forces and the solvent-solvent forces. So what does that mean? Let's look at this figure. When you have just solvent particles, so for example, let's say we have NaCl. We just have sodium chloride. We know salt. Salt is that white, it's a white crystal, right? So if I just have salt, the type of things or forces holding salt together is what? Ionic bonds. Okay. So if these are ionic bonds, those red dotted lines holding our ions together, we know these are created by a separation of charge. Okay. We know sodium is the cation, chlorine is the anion. Okay. And if we have water, as an example, what is holding water molecules together? It's based on a somewhat of a separation of charge, hydrogen bonding, okay, is holding water molecules together. So if I draw two water molecules, there's my lone pair, we know we have I'll do it in blue, a partial positive on the hydrogen because the hydrogen is positively polarized, remember, from hydrogen bonding. And I'll do black for the partial negative on the lone pairs. And so if we draw a second water molecule, we know that we're going to orient the donor of the other molecule close to the acceptor of that water molecule, the original one. And then we'll get this hydrogen bond. And again, this is all based on separation of charge, the partial positive, partial negative. So because there's a similarity there, that is the basis of polar and ionic bonds, separation of charge. Electrons are moving towards one thing, so it's electron rich, and away from another thing, so it's electron poor. And anything that's electron poor, we give that positive or partial positive charge. So because there's separation of charge, and these are the solutes, or sorry, I did that backwards. This is our solute. Salt would be our solute. Water would be our, oh man, it's not gonna let me select everything. Don't you love that? This is our, Lord have mercy. This is our solvent. Okay, sorry. Anyways, because these are similar, these two things will mix, okay? And that's what you're representing by taking, this would be like our NaCl, and this would be like our water. And those things will mix if the separate individual interactions of the two pure substances are similar, okay? Any questions on this figure? Okay. When a liquid, this bottom one down here, when a liquid is soluble in another liquid, because you can have solutions of liquids like gasoline, the two liquids are said to be miscible. So if I ask you, oil and water, are they miscible or immiscible? So the opposite of that is immiscible. Okay, if it's immiscible, then they don't mix. All right, if they're miscible, they mix. If they're immiscible, they don't mix. So oil and water would be immiscible. But an example, what would be another? Methanol, okay, and water would be miscible. Okay, methanol's acetone and water, two polar things that are both liquids. Those would be miscible. So let's do a little review here. Which of the following solutes dissolve in the following solvent? So the solute is listed first, and the solvent is listed second. Can't remember if I have a poll question for this as well. Let me see. I might. Oh, why didn't y'all tell me to take those poll results off? Let me see. No, I don't. Okay. So looking at these three, let's talk about the first one, CH4 and water. So you need to ask yourself, one, we know water's polar. It's a polar molecule. It's held together by hydrogen bonding, which is a type of bonding based on polarity. And so we just need to ask ourselves, is CH4 polar or nonpolar? If it is polar, remember, like dissolves like. If it is polar, CH4 is polar, then they would dissolve. They would mix. You would get a solution. But if CH4 is nonpolar, then they will not mix. So is CH4 polar or nonpolar? Well, if you draw out the Lewis structure, actually we don't even have to do that because we know it's just carbon and hydrogen. None of these bonds, based on electronegativity difference, none of these carbon-hydrogen bonds are polar. Carbon-hydrogen bond is always non-polar. And even if it was polar, guess what? We would have symmetry in the molecule. Okay. There's two planes of symmetry here, north and south, east and west. But we don't have any polar bonds, so we have a this is nonpolar. Carbon tetrahydride nonpolar. So because it's nonpolar and water is polar, no, will not dissolve. That solute, carbon tetrahydride, would not dissolve in water. Okay, look at the second one. MgCl2 and acetic acid. Acetic acid. So we need to figure out what kind of substances do we have here. What do y'all think about MgCl2? What kind of substance is that? Is it nonpolar, polar, ionic? The chat is saying it's ionic. And indeed, they are correct. How do you know this? Well, Mg, this is a metal. And Cl is a nonmetal. And remember, that is the definition of an ionic compound, a metal with a nonmetal. So that's going to be your cation, Mg. In fact, it's main group 2, so it'll be 2+. Chlorine is a minus. So this is ionic. Now remember, what do we know about ionics? Ionic stuff will dissolve in things that are polar. So the question is this solute, acetic acid is our solute, our solvent here. MgCl2 is the solute. Acetic acid is the solvent. It's the liquid here. Is it polar or nonpolar? What do you guys think? Well, we could draw out the Lewis structure. And acetic acid, this is actually probably from this, it might be hard to draw, but we've got 2 carbons. We've got 4 hydrogens here, and because this is an acid, this hydrogen, this is not a condensed structure, by the way. How do we know it's not a condensed structure? Because we never see carbons put together like this in a condensed structure. So because it's not a condensed structure, it's a little bit more difficult to draw, but acetic acid looks like this. Okay, here is acetic acid. So what do y'all think? Is this polar or nonpolar? It's definitely polar. Okay, carbon and oxygen bonds. So these bonds right here, this bond right here, these are polar bonds. And this carbon hydrogen bond is all polar. And there's no symmetry in the molecule. So could we draw a dipole in, pointing from the partial positive portion of that's a lot of P's, of the molecule towards the partial negative portion, the electron dense portion of the molecule? Absolutely, we could. Let's do that. I just like to draw them kind of across the whole molecule. If we split the molecule in half, the left side would be the partial positive region, the right side would be the partial negative region, okay? Because of all these oxygens and all their lone pairs. So we have an ionic solute in a polar solvent. Will this dissolve? Would you get a solution? Jenna says yes. Anybody agree, disagree? I'm seeing some head nods. Okay. Yes, you would. It would dissolve. All right, now let's look at CH2Cl2 in methanol. CH2Cl2 in methanol, okay? So what do y'all think about this? CH2Cl2. CH2Cl2 in methanol. So this is our solute. So what's going to be dissolved in methanol is our solvent. So first off, CH2Cl2, polar or nonpolar? Jenna says polar. Y'all think it's all polar? Okay. Here's the deal. This one actually is tricky. Let's look at this. We have a carbon. It depends how you draw this. So let's draw it. I'm going to draw it 2 different ways. We know carbon has 4 bonds. 2 chlorines. What if I draw it like this? Or what if I draw it like this? We know those chlorine have lone pairs. Here's what you have to know. Molecules, unfortunately, we have a disadvantage here. We're looking at a two-dimensional drawing. Molecules are not two-dimensional, they're three-dimensional, remember? We talked about geometry. So these things can rotate. So in fact, if you can draw it in a way that it is nonpolar, that thing is nonpolar. Okay, because we don't see, sure, if we rotated the structure, we might get it to look more like this, but it's just a matter of rotating it and how we're looking at it in 3 dimensions. But we can't look at these in 3 dimensions, unfortunately. We can just draw them on paper. So if you can draw it in a way that it is nonpolar and dipoles cancel, then that substance is nonpolar. It looks like the structure over here on the right looks like you would say, oh, it's polar. But if, in fact, if I had this in 3 dimensions and I just rotated it, I could get it to look like this. And this is a nonpolar molecule because the dipoles, if these carbon chlorine bonds are polar, and so we could draw dipoles pointing towards chlorine. And guess what? Those dipoles cancel out. So CH2Cl2, that's why I think it's important to draw the Lewis structure, even for simple molecules. This is nonpolar. And methanol, this one's a little more straightforward. No guesswork here. Less guesswork, I should say. There's our structure for methanol. And this is absolutely polar, okay? Because, well, you have two different bonds that are polar. You got this one that's polar and this one that's polar. And you got lone pairs as well. And so because of all of that, if we drew a dipole in on this molecule, it would point towards the oxygen side. This would be the partial positive side. This would be the partial negative side of the molecule because that oxygen and those lone pairs. So here's what we have, a nonpolar solute and a polar solvent. So guess what? Nope. Would not dissolve, would not mix. So that one was a little tricky, okay? Going back to y'all's word, tricky. All right, any questions on what we just did? This kind of stuff definitely could be an exam question, okay, for exam 4. If I gave you multiple choice and said, here's, the first one's A, B, C, or D, I had another option. And I said, which one would mix or which one didn't mix? This is the style of question. This is how I'd want you to look at it and answer it, okay? All right, so just to help you guys, I think it would be helpful, not that you have to memorize these, but just to have a list of common polar solvents and common nonpolar solvents. That way, if I do give you an exam question on these, you can recognize it, and maybe you not even have to draw them out if you already know which ones tend to be more commonly polar and which ones common names for nonpolar solvents. So polar, let's get polar first. Common polar, well, the first one, anybody know what I might write for the first one? The most common? Yeah, water. Yep. Water is the most common common polar solvent. Okay, another one though that we looked at in the problem above was acetone or acetic acid, sorry. All right, what was the structure for acetic acid? It was, I'm just going to draw it out for you. Okay, acetic acid is a very common polar solvent. Another one was that third one down here, methanol is polar. That's a very common polar solvent, which is CH3OH, and acetic acid was the H, C2H3O2. And I'll give you one more, ethanol. Ethanol is similar to methanol, it just has another carbon group. So it'll be CH3CH2OH. So methanol is CH3OH, ethanol just has another carbon group, CH3CH2OH. And we'll actually get to this in chapter 12, but anytime you have an OH group, remember this is a hydroxide ion. This was from your polyatomic list. Hydroxide, you call a molecule with an OH group in it, you call the name ending is OL. So methanol, the fact that you have that OL ending indicates that there's a hydroxide ion there. And we'll learn this with the chapter 12. This is functional group stuff. So no, you don't have to remember these names, but I do want you to recognize these common polar solvents. Okay, common nonpolar solvents. Let's see. One common is carbon tetrachloride. You guys remember how to name? Sorry, question in the chat. Does that mean any solvent with an NOL ending is polar? Unless there was some kind of symmetry in the molecule. So I can't think of an example right off the top of my head, but I mean, if you had, and I don't know how we would name a molecule like this. This goes back to organic chemistry, and it's been a minute since I've fully done a lot of organic. If you had a molecule like this, okay, then there's symmetry there, even though there's OH groups. Again, I don't know how we would name this, but that would be nonpolar because those dipoles would cancel. But if there's just one OH group, then yeah, for sure it would be polar. Okay, carbon tetra chloride, which is CCl4. This is a very common nonpolar. Even though the bonds, carbon-chlorine bond is polar, this has a lot of symmetry in it. So any dipoles that we would draw in would cancel. Okay. Carbon tetrachloride. Benzene. So you're like, what in the world is this? Benzene. This is just a carbohydrate, C6H6. Can anybody think about how this would look? C6H6. Benzene. It's a very non-polar, so it would mix with like oil. This is an organic. A lot of organic chemists use benzene to dissolve stuff. It's actually a ring. It's like a hexagon if we are an organic, which I'm not an organic chemist, but it would look like this. Carbon connected to carbon, connected to carbon. Just make a ring of them. And then each of those carbons, well, and actually I think there's double bonds in our structure like that. And then each one would get a hydrogen. Crazy, huh? So anyways, it's nonpolar. There's all kinds of symmetry here, but all the carbon hydrogen bonds, those are all nonpolar. So benzene, and then diethyl ether. All right, what does this look? Diethyl ether looks like this. One more. All kinds of symmetry. And you do have this oxygen in the middle, but because there's symmetry there, these are common nonpolar solvents. So that's, again, you don't have to like memorize all these things, but I think this will help you on style of questions like above. If you could quickly glance at this list and say, oh, do I have one of these solvents? Is it polar, nonpolar? Therefore, then all you're trying to do is identify what kind of solute you have and if it is therefore polar, nonpolar, if it would mix or not. Any questions on these? All right. Okay, now we're at solubility limits. So I mentioned this earlier, but when you figure out that something will dissolve, there's only so much of it that can dissolve in a certain amount of solvent. So for example, salt and water. I believe the solubility limit is like between 32 and 36 grams of, I'm going to misquote myself here. Grams of salt in how much water? What was the amount of water? Solubility limit of, 36 grams of salt in 100 milliliters of water. Okay, if you try to add more than 36 grams, you're going to just see the salt start to settle at the bottom. But that's quite a bit. 36 grams is quite a bit. But to any solution, there's a limit of how much of the solute you can put in the solvent. Now, the max amount of solute that can be dissolved in a solvent is called its solubility. That is the solubility of the solute. And it's usually expressed as, just as we wrote up here, grams of solute per 100 milliliters of solvent. So just as we wrote with the salt in the water up above, the grams of solute per 100 mils of solvent, that is usually how solubility is expressed. Once the max amount of solute is dissolved in a given solvent, the solution is said to be saturated. Okay, and here is what is actually happening. We're going to talk about saturated solutions in just a second. I'll give you a really good example. Here's what is happening when we're dissolving something. This right here, if we look at this big purple and green cube, it is sodium, cation, chloride, anions. Okay, and we know ionic compounds are very ordered and arranged. The anions and the cations are together in a very ordered manner. And then we have these water molecules, which are the red and white molecules. And what happens when you dissolve something is water molecules are going to interact with this salt crystal, and the partial negative portions of the water molecule, so the oxygen, which is the red sphere, are going to be really attracted to those sodium cations because they're positively charged. And they're going to surround themselves just like this on that sodium cation, the purple sphere. But the chlorines, the chlorides, we know they're negatively charged. The green spheres are negatively charged. All right, so let me see if I can do like a white. These are positively charged, and we know the chlorines are negative. So the opposite side of the water molecule, the partial positive side of the water molecule, which is the hydrogens, are going to surround the chlorine cations. And once you get enough interactions between the ions, sodium or chloride, and the water molecules, they're going to break away with the water molecules. Okay, and then you have ions that are dissolved. Okay, but eventually you run out of water molecules. Okay, if you put enough salt in there, you'll use up all your water molecules and they'll all be dissolving their own ions and you can't dissolve anymore. Okay, that's when you get a solution that is saturated. So anybody like to buy like really local honey, or you've had a bottle or a jar of honey before? And what happens sometimes when you leave that honey over a long period of time? What can happen? What happened to the chat? Check. There it goes. It crystallizes. Yes. Caitlin said it crystallizes. And that's always very frustrating then, because you have to go microwave it, okay, or something if you want to mix all that sugar. So honey contains tons and tons of sugar, and that sugar can crystallize at the bottom because honey is an example of a saturated solution, the sugar being the solute. So there's so much sugar in honey that it can crystallize, and actually honey is an example of what we call a supersaturated solution. There's more than the amount that can stay dissolved. And if you have a supersaturated solution, then the excess honey that really can't stay dissolved will crystallize at the bottom. But there are ways we can manipulate solubility. We'll talk about those in a second, so that you get things like that to dissolve again. So talking about dissolving, or the dissolution of a solute, dissolving of a solute into a solvent. Remind me, is that a physical or a chemical change? This goes way back to like the first week of class. We talking about physical or chemical changes here? Physical, question mark? Yes, physical. These are physical changes. We're not creating a new substance. We're just mixing two substances. So we're not modifying any reactants or product and getting new products. We're just mixing two things together. And we still have the two things. They're just now redistributed. And that is an example of a physical change. Okay. So we have all these rules with solubility and solubility limits, but kind of like with any good rule, there are ways to bend it or break it. Anybody in here, you would consider yourself like a very strict rule follower? Do I have any rule followers? And then do I have any rule breakers? Okay. It depends the situation, if I'm a rule follower or a rule breaker, sadly. But there's always ways to manipulate or bend the rules. Here. So that's what we're about to talk about. Solubility has limits, but we can manipulate solubility with temperature. All right. So we're going to look at how temperature affects solubility and how we can change solubility. We can increase or decrease the solubility of stuff by increasing or decreasing the temperature. So first, let's talk about, we're going to either address solids in a liquid. So for example, salt water, or anybody like to drink sweet tea? We're in the South. Anybody like sweet tea? I actually don't drink. I grew up on sweet tea, but I don't drink it anymore. But some people are sweet tea diehards. And I don't know about you, but I remember growing up when I did drink sweet tea that if you go to a restaurant, you never knew if your tea was going to be like sweet enough, right? So anybody have like your little Splenda packets or whatever, and you would want to add that to your iced sweet tea. But what do you know about sweet tea that's cold, or tea that's cold, I should say, versus tea that's hot? If you were trying to dump a packet of sugar in your glass of tea, would it easily mix in a glass that is cold or a glass that is hot? Hot. That's correct. Okay. So here's what we know: solids, like the Splenda or the sugar or whatever you're mixing in your tea, solid dissolved in a liquid, solubility of the solid increases as temperature increases. Okay. The example is sweet tea. Okay. How is this an example? Sugar readily dissolves in hot tea versus cold. Okay. So the solubility of a solid solute, so salt, sugar, which is sucrose or glucose, readily dissolves in things that are hot versus things that are cold. So if you have some sugar in something that's cold and you heat it up, you could probably get it to dissolve better, or you could increase you'd have more sugar dissolve in something that's hot versus cold. So gas dissolved in a liquid. All right, let's think about this. Let's think about a club soda, for example, or any carbonated drink. Think about your favorite carbonated drink. Okay. Got some orange Fanta people out there probably. Coke or Pepsi, which one's better? Coke or Pepsi? I don't know. I don't drink a whole lot of carbonated drinks, but people have strong opinions. So think about your favorite carbonated drink. If you have that thing cold versus room temperature, and you open the crack it open, would it be more fizzy if it's cold or if it's hot? Or we should just say lukewarm. Would more gas be dissolved in something that is cold or something that's hot? That's correct. Cold. So gas is dissolved in a liquid. It's backwards. Solubility of the gas decreases as temperature increases. So with gases, it's opposite. As you increase the temperature of, for example, our soda, less and less gas is going to be dissolved in that soda. More gas is going to escape. Okay. But as you get it colder and colder and colder, the more likely the gas is to stay dissolved in the soda. For example, CO2 in water. Okay, so club soda. We'll say the club soda has more fizz, which is the gas bubbles, when cold. Okay, it's It's got more gas dissolved in it when it's cold versus when it's hot. And these next two slides are just graphical representations of exactly what we just said. So this first graph here is just if we had solid dissolved in water. So there's all kinds of solids here. Glucose, who knows what that is? Sodium nitrate, potassium bromide, copper sulfate, sodium chloride, salt. Now, these bottom two are kind of, they don't follow the trends very well, but most of these lines you can see, as you increase temperature, hotter and hotter and hotter, what happens to these lines? They curve upwards, okay? Because this is the solubility, the amount that's dissolved. So that means you climb in solubility as you climb in temperature. And that's exactly what we said here. As you, the solubility increases as the temperature increases, okay? And that's exactly what this graph is showing. And if we could read this as well. So like right here, if I ask you at 30 degrees Celsius, how much glucose would dissolve in water? Could you read that and tell me? Well, glucose is the red line. So where, if we draw a dotted line up until it hits the glucose? Okay, so about right here. And then we follow it over to the y-axis. Well, guess what? 120 grams and about 100 milliliters of, if this is water, would be dissolved. 120 gram per 100 milliliters would be dissolved at 30 degrees Celsius. Okay, so that's the solubility. So you could read this by just finding what temperature, if I ask you a temperature, and seeing where that line from the horizontal portion, the x-axis, crosses with these solubility lines for each substance. Okay, so we said at 30 degrees Celsius, how much copper sulfate is dissolved in water, or whatever the solvent is. You know, we would see where it crosses. This is copper sulfate. We'd see where it crosses the line for copper sulfate, follow it over here. Well, about 25 grams per 100 milliliters of water. Okay, so which one has a larger solubility, glucose or copper sulfate? You would say glucose. Okay. And I believe there might be a question with a graph on it for the chapter 9 homework. I'm going to have to go back and look at it. But come remind yourself of this portion of our lecture when you come to a homework question like that. And that's how you read solubility off of a graph. Okay, we know it's vice versa for grasses, different grasses. Our zoysia, our, I don't know what grasses there are. Okay, gases dissolved in water. So look at all these. What do you notice about the lines? They all tend to go down as you climb in temperature. So as you increase temperature, gases like to move. Those particles like to move. They don't like to stay dissolved. They want to have their freedom to move about, and they can do that if they're not dissolved. So as you climb in temperature, what happens to solubility? It goes down. That's why all these lines are curving downwards. So for example, the example we've been sticking with CO2, but you could also look at oxygen. It's a slight curve downwards. Really, it kind of levels out. But CO2 is a great example. If I said at 50 degrees Celsius, how much CO2 would be dissolved in, say, water? What is the solubility of CO2 in a liquid? Well, here's the 50 degrees Celsius. You would just walk that up until it hits the CO2 line right there. And then you would walk that over until it hits your y-axis. And what is that number, 20? So this looks like it's the 15 mark. So we would just say about 17.5. What are our units here? I'm turning my head sideways. Millimole per liter. Okay, so you would tell me those units. That's the solubility of CO2. About 17.5 millimole per liter at 50 degrees Celsius. Okay, so if you're asked to read solubility off of a graph, that's exactly how you do it. You just find the temperature, walk it up until you hit the line for that piece of data, and then cross it over to the y-axis, and that's your solubility. And the y-axis will always be solubility, and the x-axis will always be temperature. Any questions on how to read solubility off of a graph? Okay, I was looking at our time. We've got about 10 minutes left, and let's see. We'll cover Henry's Law, and that's probably where we will end for the day. Okay, so we'll look at Henry's Law. How many slides will we have left after that? We are about at, what slide is this? 15 of, oh wow. Maybe we'll get to units of concentration, but I'm not going to get my hopes up. So, okay, Henry's Law. What is Henry's Law? Henry's law is I'm going to say the dissolution. Actually, sorry, concentration. That's a better word. Erase that. Concentration. Which depends on how much is dissolved, but the concentration or solubility of a gas is directly proportional to the pressure of the gas when the temperature is constant. So I don't know if you noticed, but up here on our y-axis, it gave us a pressure. It said at 1 atm. If we change that pressure, if we doubled the pressure or tripled the pressure, the solubility would change. And that's essentially what Henry's law is saying, is that concentration of how much gas is dissolved in a liquid, it depends on the pressure. So what do you notice? Anytime you get a Coke bottle or a club soda can or something that has a gas dissolved in a liquid, it is sealed, and it is sealed at a certain pressure. Okay, all the factories, they add a certain pressure to that can, and then what happens when you open it? You have now changed, you've decreased the pressure. You've released it to 1 atm of if you're at sea level, okay, of pressure. And what happens? A lot of gas, all of a sudden, you see it bubble and kind of fizz. A lot of the gas is escaping because you've lowered the pressure. It was pressurized in that can, but when you open it, you've decreased the pressure, and so a lot of gas will escape. So the more pressure you add, the more gas will dissolve. That's what Henry's law is saying. So pressure affects the solubility of gas in a liquid. So if you increase pressure, you're going to increase gas solubility. So the more pressure you put on any sort of container that has a gas that's on a liquid, the more of those gas particles will dissolve and go into the liquid. So here is the mathematical representation, kind of like Boyle's or Charles or Gay-Lussac's law. Here's how Henry's law looks. C stands for the concentration of the gas. Now, let me tell you something here. The units for concentration are, remember, gram. Concentration is essentially, or solubility. So the units for our solubility are gram per 100 ml. Those are the units. So this is going to get a little bit different. We haven't seen something like this before. We're going to work through an example problem. But those are units for the concentration of how much gas is in the liquid. And then P is pressure. So you have C1 over P1 equals C2 over P2. So remember, the 1 stands for the concentration and the pressure initially at your initial conditions, and the 2 is at your final conditions. So look at this figure. Here we have some sort of equilibrium. Okay, so we have, what are these arrows representing? You have these red spheres. These are our gas particles. And what do you notice? They're all flying about and they're moving about. Even down in the liquid, they're moving about. And you have some gas particles that are escaping up into the air, okay, above the liquid, and you have some that, are casually dissolving. So it's back and forth, and that's what equilibrium is, back and forth. And it's equal, okay? The gas particles escaping versus the gas particles coming back into the liquid are equal. Well, what if we increase the pressure? What if we push down on that lid? What you're seeing is many more downward arrows compared to upward arrows. So that just means more gas particles are going to dissolve into that liquid the more pressure you put on it. And then eventually equilibrium will be restored, okay? But you notice in this picture over here on the right, we have way more red spheres, which are the gas particles, dissolved in the liquid because we have increased the pressure, right? So that's essentially compared to over here. Fewer gas particles in the liquid, more. So if you just increase the pressure, you're going to increase the amount of gas particles dissolved. Now, how does this play into health sciences? How does this affect us? Well, we know blood is a solvent to a lot of things, with oxygen being one of them. I'm going to turn my screen and we're going to work this problem, and that might be all we have time for today. But so this is a problem, an example of Henry's law at play. A lot of you alluded to this when you used your bonus point opportunity. You talked about oxygen in blood and things like that. And so here's a practice problem. So when the pressure, P of oxygen. What does this mean? P of oxygen, just this, the pressure of oxygen in the blood. Okay, it is 159. What is mmHg? Remember, that is a unit of pressure. That is millimeters of mercury. Okay, millimeters of mercury from that little barometer instrument we talked about. So when the pressure of oxygen is 159 millimeters mercury, the solubility of oxygen in the blood is 0.44 grams per 100 milliliters of blood. So that's 0.44 grams of oxygen per 100 milliliters of blood. Okay, but altogether, this is how much oxygen is in the blood. So that's the concentration. So essentially, this is C1, because remember, concentration has units of grams per milliliter, and this is P1. That's the initial, that's the pressure, the blood pressure at that concentration of oxygen. Now, what it's asking is, what is blood solubility, or the concentration of oxygen in the blood? So we're looking for C2 at a new elevation, because we know pressure changes with elevation, right? That's Boyle's law. Or no, that's Gay-Lussac's law. No, pressure and I don't know which one it relates to. This may be different. But we know that pressure changes at elevation. Okay, so at 11,000 feet elevation, where the partial pressure of oxygen has lowered now. So this is our P2, 56 millimeters of mercury. So let's use Henry's law and let's solve for C2. We know it's C1 over P1 equals C2 over P2. So we're going to plug the three pieces that we have in, and we're just going to solve for C2. But first, we need to rearrange our equation. I'm going to slide this over just a second. So let's rearrange our equation to just get C2 by itself. And to do that, I'm just going to cross multiply both sides by P2. So this is a lot of what you would do with those ideal or the gas laws. We had a couple of those on the exam 3. And you just had to rearrange your equation. So our new equation is P2 times C1 over P1 equals C2. So now we're just going to plug the pieces in. And here's what you're going to be tempted to do. Look at units on concentration. It's grams per 100 ml. And you're going to treat all of this as the unit. So you're not actually going to divide 0.44 by 100. You're going to leave it. It's weird. We've not had units like this before. You're going to leave the 100 milliliters as a unit. You're not going to divide by 100. Okay. It's a unit. It's part of your units. So here's what that looks like. P2, where's P2? 56. Okay. So I'm just going to come over here. 56 millimeters of mercury times C1. Where's C1? Okay. That is our initial, I wrote all over it, but here's our C1. 0.44 grams per 100 milliliters. So 0.44, and these are all units, gram per 100 milliliters. You're not going to divide by that 100. And then on the bottom is P1, which is the 159 millimeters of mercury. So notice units of millimeter mercury cancel out, and we are left with units of gram per 100 milliliters. So we do 56 times 0.44 divided by 159. (56 times 0.44 divided by 159). Anybody have that? 56 times 0.44 divided by 159. And I got, okay, Tia got it as well. She got 0.155. It's exactly what I got, Tia. So it'd be grams per 100 ml. That's your units. Do not divide by that 100. So you can see as you increase in pressure, or as you decrease pressure, what happens to the solubility of oxygen in the blood. Initially it was 0.44 grams, and now it's 0.15. It's about a third. The solubility of oxygen decreases as you increase in elevation. That's why sometimes, you know, extreme hikers, people who want to hike Mount Everest or whatever, they have to take oxygen tanks with them because they may need to add more oxygen to their blood the higher you climb in elevation. All right. We're going to pick up with units of concentration on Tuesday. So I was really hoping to get further, but we'll pick up here on Tuesday.